The journey should start to make a little bit more sense for you now. However, for those of you that are joining us for the first time, don't worry, you won't be left behind, because we are going to have a very, very brief recap of some of the basic principles that we've looked at in the previous weeks. So just a little bit about Spirax Sarco. We are a global organisation with our headquarters here in the UK. And as far as the UK and Republic of Ireland division is concerned, we're a team that's about 200 strong. Approximately 50% of that team is based remotely. We're scattered across the UK and Ireland, so we're always on hand to offer you and your colleagues assistance should it be required. But if you look over towards the right-hand side of the screen, hopefully the links and the little icon you can see up in the top right-hand corner really demonstrate that we've got a lot of resources available, both in the form of online tutorial and online calculators. However, we've also got a very, very powerful source of tools and resources and configurators that are available in the form of an app that you can download to your iPhone and smartphone. And you'll find those particularly useful whenever you're calculating the impact of steam in financial terms, but also if you're looking to size solutions such as control valves, steam traps, and in fact, heat exchangers, which we're going to come on and discuss in a little bit more detail as we go through the presentation. So 4 weeks ago, we started off with our journey, understanding the basic first principles and the fundamentals of steam. We also looked at how steam is generated in the boiler house, and hopefully what you'll take away from that presentation is the importance of understanding how dry the steam is. And 2 weeks ago, we moved forward with our journey to understand how we need to apply good working practice to ensure that the steam is moved from the point of generation to the process so it can arrive quite often thousands of meters away from the boiler house in the best possible condition. And of course, once we get the steam to those various processes around site, we're going to use the steam for a number of different things, but most often and most frequently, that steam is going to be used for heat transfer or for heat exchange. So whenever we're talking about using steam for heat exchange, well, we can use that steam in solutions that we refer to as heat exchangers. Essentially, it's to allow the heat energy in the steam on the primary side of the heat exchanger to give up its energy to the process on the secondary side. So there's an exchange of heat, but it means that we don't have a risk of any moisture or other potential contaminants that may be present in the steam affecting the process on the secondary side. There's an exchange of heat energy, but nothing else. So a heat exchanger, well, it's a term that can extend to shell and tube heat exchangers, to plate heat exchangers, but it can also refer to a far, far wider range of solutions, such as reactors that can be used in the pharmaceutical and biochemical industry, to jacketed vessels that can be used in the food and beverage sector, and also to air handling units that may be using steam coils to heat up the incoming air. So on today's presentation, we're going to look at why steam is so popular for so many different heat exchange applications. And we're also going to look at the considerations that we need to give to steam that are completely different to using other media such as low temperature hot water or thermal oils on the primary side. So we're going to look at the issues that are unique to steam heat exchangers, such as stall and condensate removal, for example. So the steam tables that we've gone through previously, they really give us a lot of very valuable and very, very useful information. And you'll remember that the steam tables have got their basis on the understanding that water, the raw ingredient of steam, that's got a specific heat capacity of 4.19. In other words, if we want to increase the temperature of 1 kilogram of water by 1 degree, we need to put 4.19 kilojoules of heat energy into it. So let's take the example of generating steam at 0 bar gauge pressure, for example, in your kettle at home. So at 0 bar gauge, we know that water boils at 100 degrees. If we multiply that 100 degrees by 4.19, that tells us we need to put 419 kilojoules of energy into that water before it boils and starts to change state and produce steam. We refer to that as the sensible heat, and that's demonstrated in the third column along from the left. The sensible heat, also known as the enthalpy of water. But we don't want boiling water, we want steam. And we need to add 2,257 kilojoules of energy into that boiling water to make it fully evaporate and change state from a liquid to a gas. The enthalpy of evaporation, that's also known as the latent heat energy. And together, they've got a total heat of 2,676 kilojoules. And you can see that once that kilogram of water has changed state and produced a kilogram of steam, its volume has expanded significantly from 0.001 cubic meters when it's a liquid to 1.673 cubic meters when it's a gas. So it's important to understand that when steam gives up its heat energy, it does so by condensing. It changes state from a gas back to a liquid again. And when steam condenses, it gives up its enthalpy of evaporation. In other words, it's that latent heat energy. It's the energy that we added to the boiling water to make it evaporate. That's the heat energy that can be used by the process, that's demonstrated in that middle column with the little green oval. That's the useful heat energy. So that means when steam gives up its heat energy and condenses, it gives up its latent heat. That liquid condensate, the byproduct of heat exchange, if you like, that still retains 419 kilojoules of energy. That's the sensible heat. So the energy in the condensate, that sensible heat, that cannot be used in the vast majority of heat transfer applications. It's simply got no value to us. In fact, we need to get it away from the heat exchanger, because if it starts to flood the heat exchange space, then we simply can't get enough of that energy rich steam into the heat exchanger. And of course, the process time will extend and extend. But if you look very, very closely, you'll see that when steam condenses and gives up its heat energy, it gives up its latent heat. The condensate retains the sensible heat. There's an exchange of energy, but there isn't an exchange of temperature. The condensate will exist as a liquid at exactly the same temperature as the steam does. And the first two columns really demonstrate that pressure to temperature relationship. In other words, if we've got a heat exchanger that is condensing steam at a pressure of 2 bar gauge, we know that the temperature of steam at 2 bar gauge is 134 degrees, and therefore we know that the temperature of the condensate at those conditions will also be 134 degrees. The condensate can exist as a liquid at that point because of the pressure. So we've also spoken about the temperature enthalpy curve previously as well, and this really demonstrates the journey that water takes as it changes state from a liquid to steam as a gas. And we've emphasized previously that if we're generating wet steam in the boiler house, we expect to have a number of different issues. First of all, wet steam, as it travels around the distribution network, is far more likely to change state to condensate. And if we get an excess of condensate in the pipework, well, we're likely to encounter a starvation of steam at the process. So it's inevitable that there's going to be a delay in which the energy can pass into the process. The heat exchanger could be undersized. It means we've got to live with a longer and longer process time, more condensate in the pipework, you'll remember we're likely to encounter more mechanical issues such as that erosion, the corrosion, and the water hammer. But this particular presentation, we're focusing on steam and heat exchange. So we know that if we've got wet steam, the steam is going to exist with far, far less energy contained within it when it's wet compared to that dry saturated steam. And the problem we have is that the steam tables, which are the basis for sizing and selecting the appropriate heat exchanger for the process, they're all based on the assumption that we're getting steam that is 100% dry and therefore with the maximum amount of heat energy present within it. So we also know that apart from those very, very valuable fundamentals that make steam a very, very attractive source of heat energy, remember, steam's got in many cases up to 50 times more heat energy per kilogram when compared to low temperature hot water. Remember, steam gives up its heat energy evenly and equally across the heat transfer surface area. And remember, there's a speed of heat transfer that is approximately 3 times that of low temperature hot water, for the simple reason that steam gives up its heat energy by condensing. But what the little image up in the top right hand corner is trying to demonstrate is that the fact that the steam uses all of the heat transfer surface area efficiently. And the little image, well, it's a sauna. So for example, if we were putting 2 or 3 kilograms of steam into that space, that steam would start to spread out and occupy every corner of the sauna equally and evenly. Whereas if we were to put 2 or 3 kilograms of water as an alternative into that sauna, well, it'd sit on the floor as a puddle. It wouldn't utilize that heat transfer space very efficiently at all. We get striations, we get cold spots. And it's a little bit like understanding the inefficiencies caused by failing to bleed your radiators at home. Well, we simply don't have that issue using steam because it's a gas. It's not a liquid that falls due to its density to the lowest possible area of the heat exchanger. And we also know that because steam gives up its heat energy by condensing, well, the process, the heat exchanger, it will only draw the energy in the steam towards the process as and when required. So I just want to remind ourselves that when steam's being used to heat a process, it's that enthalpy of evaporation. It's that latent heat energy. It's the energy that we added to the water that was already boiling to make it change state. It's that latent heat that is used for heat exchange purposes. And that's approximately 75% of the total heat energy in the steam. So remember, the total heat energy of the steam, it comprises the useful heat energy, the latent heat, but it also comprises the heat that we cannot use, the sensible heat that's retained in the condensate. Now, that doesn't mean to say that a heat exchanger can expect to have an inefficiency of 25%, because what you'll remember from the previous presentations we've gone through is that hot water, that condensate, it can be used efficiently if we get it back to the boiler house and keep the water in storage in the feed tank at a nice high temperature. So it does have a use, it's just not useful for heat exchange purposes. And just as steam's got that direct pressure to temperature relationship, so too does the condensate. So just coming back to that pressure to temperature relationship that we've spoken about in previous presentations, the steam saturation curve that you can see on the screen now, it demonstrates that if we're generating steam at a nice high pressure 10 bar gauge, we know that the temperature of the steam is 184 degrees. And because condensate has got the same pressure to temperature relationship, that means the condensate that is going to exist in the distribution steam pipe, where we're distributing the steam at that nice high pressure, the condensate will exist as a liquid at 184 degrees. But if we've reduced the pressure of the steam at the process down to 2 bar gauge, well, we know the steam and the condensate will exist at that point at 132 degrees. So it really demonstrates by manipulating the pressure, we're actually controlling the temperature. So when we're talking about using steam for heat exchange purposes, that pressure to temperature relationship and the fact that the energy will only flow from the steam onto the heat exchanger as the heat energy is required by the process, it means that we only need that 2-port valve to control the flow of energy from the primary side to the secondary side. And in fact, it can be a self-acting valve. It doesn't have to be an electrically or pneumatically actuated valve. We can perform that function very, very easily with a basic control valve or a basic self-acting valve. So think about the benefits that brings to a steam system compared to a water-to-water process. A water-to-water process, water-to-water heat exchanger, is going to require a 3-port valve. Can't use a 2-port valve because water doesn't give up its heat energy by condensing. And it means that we therefore need to divert any energy that isn't required by the process away from the heat exchanger. So we need a 3-port valve with the 3rd port being the diverting leg. And it also means that because steam is a gas and moves in accordance with the pressure drop, we already understand that we don't pump steam. It flows in accordance with the pressure drop. But of course, we need to pump that liquid. So that water-to-water heat exchanger, it will require a little circulating pump on it to ensure that any unwanted energy can pass quickly away back to the boiler house. So that means a heat exchanger skid that's utilizing steam is not only going to be a little bit cheaper to engineer, it means that we can break down the heat energy in the steam more rapidly and more efficiently. So I'm just going to play a little GIF now that really shows how those benefits that are present in the steam can really tie together to add a number of benefits to any process that may be considering using steam as an alternative to other sources of energy. In this example, low temperature hot water. So the first thing we need to do with a steam heat exchanger is ensure that that air can be vented away to ensure that all of the energy can be present and we're not going to have the insulating effect of any air present. Remember, we don't pump the steam, it moves in accordance with the pressure drop. And remember, we've got a very, very high speed of heat transfer with steam compared to low temperature hot water. The steam will condense equally and evenly, meaning we're not going to get cold spots or product spoilage. And ultimately, it means that we can bring the process up to temperature far, far quicker than we can with water because there's far more heat energy contained within it, and it's easier to control because we can control the temperature of the steam simply by manipulating the pressure. So moving forwards, what we can see on the screen now is the 3 basic thermodynamic equations that apply to the sizing and selection of heat exchangers. Now, of course, there are a number of different thermodynamic equations. We're only going to look at the 3 basic ones that apply to plate heat exchangers today. So if we look at the 3 equations, the equation at the very, very top, that applies to the far right of the process diagram we can see towards the right-hand side of the screen. It's the process side. And what you'll see is if we want to determine the amount of energy that is required to heat a process, we need to know a number of variables. So first of all, we need to know the mass flow rate of fluid that we want to add that heat energy to. Of course, we can calculate that, or that can be given to us by the steam user, the process owner. We then need to multiply that by the specific heat capacity of the media that we're adding that energy to. In the case of water, that specific heat capacity, you may remember, is going to be 4.19. And we then multiply that by the temperature rise required. The example you can see on the screen, we need to add 20 degrees to that water. So we calculate the heat transfer rate simply by multiplying the mass flow by the specific heat capacity by the temperature rise. Relatively straightforward. And then if we want to size the heat exchanger, well, we calculate the heat transfer rate by multiplying the heat transfer coefficient. That's the speed of heat transfer. We refer to that as a U value. Now, that heat transfer coefficient, that would typically be badged on any existing heat exchanger that we'd be working with, or we can find it from the manufacturer's thermal energy data sheet. If we're looking at a new heat exchanger, then we can go back to first principles and we can calculate that U value. We then need to multiply that by what we refer to as the A value. And that's the heat transfer surface area itself. So in the case of a plate heat exchanger, then we'd add up the effective area of the plates, we'd multiply it by the number of plates to determine the area. In the case of a shell and tube heat exchanger, it would refer to the surface area of all of the tubes that were involved within that bundle, that tube nest. Again, the A value, the area, that will typically be badged on any existing heat exchanger. We can find it from the thermal energy data sheet of the manufacturer, or again, we can go back to first principles and we can calculate it. And we then multiply that by the temperature difference of the primary media and the average temperature on the process side. Now, if we're using steam, remember, we can determine the temperature of the steam if we understand the pressure that the heat exchanger has been designed to work at. So in the example of 3-bar gauge, we know that steam at 3-bar gauge has got a temperature of approximately 143 degrees. And the average of the process temperatures, you can see, is 80 degrees. We can then move across to the primary side of the heat exchanger that's demonstrated by the bottom equation on the page, and we can determine the heat transfer rate that's required on the primary side to satisfy the process by multiplying the mass flow rate of steam in kilograms per hour by the enthalpy of evaporation. That's that latent heat energy, the useful heat energy that is present within the steam if we know the pressure. And on this occasion, you can see that we've determined that we've got steam at 3-bar gauge pressure going on to the heat exchanger. So they're the 3 basic thermodynamic equations. And one of the basic fundamental laws of thermodynamics states that energy cannot be created or destroyed. It only moves from one form to another. What that actually means is if we've calculated the Q value in any one of these 3 equations, we can simply carry it across. The heat transfer rate will remain the same. So if we've calculated the Q value for the process, it's going to be the same as the Q value on the primary side and the same as the Q value for sizing the heat exchanger. So that means we can use that information to transpose and rearrange those equations. So if any of the values on the screen that you can see are unknown, we can simply transpose the known values in the equation to calculate the unknowns. So as far as steam to water heat exchangers are concerned, it's that U value that we spoke about. It's the speed of heat transfer that's one of the most interesting things. And hopefully you can see that the U value, or the heat transfer coefficient, the speed of heat transfer with steam, is about 3 times that when we compare it to a water-to-water heat exchanger. And that's because steam gives up its heat energy by condensing, which of course water doesn't. And compare that with the fact that steam's got approximately 50 times more heat energy contained within it compared to the same mass of low temperature hot water. High energy content, and it gives up that energy very, very quickly. So if we've got a very, very high U value, by referring to the equation above, you can see that that means, as a consequence, we need a much, much smaller A value. We need a much smaller heat transfer surface area to satisfy the process. So the benefit there is, not only does it mean that we require a smaller heat exchanger to satisfy the process compared to water, that's going to be less in cost. It's going to take up a much, much smaller footprint in the plant room. It also means we're going to get far, far fewer thermal losses. We're going to get less heat energy radiated out into the plant room. Now, traditionally, steam or hot water was generated from steam relatively slowly over a period of time. And that meant that any hot water that was produced had to be held in storage in a buffer vessel on the secondary side. But now we can harness all the attractive qualities that are present in steam to generate hot water or other processed fluids instantaneously and on demand, meaning we can eradicate that buffer vessel altogether. So I just want to go back to the steam tables once again. And you'll see in the case of generating steam in that kettle at home at atmospheric conditions, well, you'll see that the energy content that we need to add to the water to make it boil is relatively small, 419 kilojoules of energy. But we need to put a considerable amount of energy into the water to make it change state and produce a gas. So the total heat energy content is relatively low. And that's because we've got a low sensible heat, slightly higher enthalpy of evaporation, but it means we've got less total heat energy present in the steam. But if we increase the working pressure, you can see that we need to put significantly more energy into that higher pressure water to make it boil, but less energy into it to make it change state. But those two heat value properties together combined means that steam at a higher pressure has got more total heat energy contained within it. So we went through the reasons why 2 weeks ago we generate steam at a high pressure. Higher pressure steam, it means that there's more motive energy in it for distribution to the processors. It also means it's likely to be drier and of a better condition, but it also means we can distribute it in a much, much smaller and therefore more cost-effective pipework. But remember, for heat exchange purposes, it's that enthalpy of evaporation in the middle column. That's the useful heat energy. And what you'll see is at 10 bar gauge, a kilogram of steam has got 2,000 kilojoules of energy present within it. But if we can reduce the pressure and condense the steam at 0 bar gauge or as close to 0 bar gauge as we can, we've got significantly more energy present within it. So it's a no-brainer. We want to generate and distribute the steam at a high pressure, but the first thing we want to do when we get the steam to the process is ensure that the heat exchanger has been sized to condense the steam as low as possible. It means that we get a far, far greater efficiency of heat exchange, we get a greater speed of heat exchange, and ultimately it means that we're not adding too much energy or too much temperature to the process, which could end in product spoilage as well. So there's also a rule of thumb that we can apply to steam systems being used for heat exchange, and that's that if the process requires 1 kilowatt of energy, then we know we need to supply it with 1.8 kilograms of steam. And conversely, if we've got 1.8 kilograms of steam available, we know it's capable of adding 1 kilowatt of energy to the process. Now, that rule of thumb, it should only really be relied on as a very broad and high-level sanity check. It doesn't take the place of the steam tables, and it doesn't take the place of going back to first principles and using those thermodynamic equations. It's simply there as a sanity check. So we've mentioned already, steam gives up its latent heat energy by condensing. So the byproduct of that heat exchange is that liquid condensate. So above you can see what we'd refer to as a closed loop heat exchange system. And that's where the steam goes onto the heat exchanger, it gives up its heat energy, and that liquid condensate's got to be drained away because it can't be used for heat exchange purposes. So it bears mentioning that steam, it can be used for direct injection purposes. That's where the steam enters the atmosphere or the process, and therefore the condensate does too. Both the latent heat and the sensible heat go into that atmosphere or process. So in those cases, there simply isn't going to be any condensate to be removed anyway. So an example of a closed loop system is going to be a jacketed vessel or a shell and tube heat exchanger or a plate heat exchanger. It's where we need to separate the steam from the condensate after that heat exchange has taken place. So one of those traditional heat exchangers that we've spoken about that has up until relatively recently use steam to generate sources of hot water and then hold that hot water in storage on the secondary side until it's required, also referred to in many applications as a calorifier. Traditionally, it's brought our clients a peace of mind that that buffer vessel means that they've always got a supply of hot water that's there ready and waiting for them. But that volume of hot water that's held in storage can also bring a significant number of challenges that can quite often be overlooked. And that's because if we're holding hot water in storage under pressure, it's going to fall under the Pressure Equipment Directive. If we've got a volume of hot water under pressure at a high temperature, we've got the Legionella issue. And that's going to bring not only a certain amount of risk, but it also means that we're going to need periodic insurance inspections and maintenance concerns that are all going to come with some cost and a little bit of downtime whilst that maintenance and those inspections are taking place. But it also means we're going to have a fixed vessel. It means not only is that storage vessel a fixed size, but the tube bundle assembly is also going to be a fixed size. That A value that we spoke about is going to be fixed. And it bears mentioning that a tube bundle assembly, if we laid it out on the floor, it'll take up a significant footprint of space. And that's one of the reasons why storage heat exchangers will take up a significant space in the plant room. But even though it's got a very relatively large footprint, it's got a very low surface area, a low A value. Whereas if we compare that with a plate heat exchanger, if we've got a number of plates all stood up on their end, it takes up a very small footprint of space. But if we laid the plates out side by side on an area across the floor, well, you could appreciate it'd have a very large A value or a large heat transfer surface area. So hopefully you can start to appreciate how those thermodynamic equations mean that we can now use all of the excellent properties of steam, the high energy content, the high speed of heat transfer, that U value, and the fact that steam gives up its heat energy evenly and equally, very efficiently across all of the heat transfer surface area means that we now also need a very, very small A value. In other words, we can generate hot water from steam instantaneously and on demand, meaning we no longer need that buffer vessel of hot water in storage. So I just want to very quickly look at a typical application. I'm going to use the example of a hospital. Of course, we can use heat exchangers in countless processes, but hopefully a hospital is one that we can all relate to. So hospitals are huge consumers of hot water, not just for domestic, but also for heating purposes. And if we were calculating a typical demand for hot water in a hospital, then we would calculate all of the draw-off points around site, all of the areas where hot water can be consumed. And we can then refer to a typical sizing methodology, such as BS-EN 806, and that determines that different draw-off points they'll consume hot water at different rates. So we'll calculate what we refer to as a loading unit, and that will give us enough information to size a heat exchanger with a reasonable amount of accuracy. But the problem we have is that if we've got a client, whether it be a hospital or any other process, if they're calculating a new heat exchanger requirement, then it could well be that we're at danger of oversizing the heat exchanger. So there could be a little bit of inaccuracy in inefficiency there. But this is the best methodology that we have, really. What we want to ensure is if we're helping a client move away from an existing storage heat exchanger to move towards a modern and efficient instantaneous plate heat exchanger, perhaps the very worst thing we can do is to take the badged duty off the older heat exchanger and carry it across to the new heat exchanger. We'd simply be duplicating any inefficiency. And in examples such as that, perhaps the best thing to do would be to fit a makeup meter on the cold water feed, because that way we'd be able to exactly match the hot water requirement and then size any new heat exchanger appropriately. Now, as far as those older storage heat exchangers are concerned, they're going to bring our clients a number of different operating challenges. For one, we're holding that hot water in storage. And because the heat exchanger is likely to be oversized, could well be that the process has changed over a number of years, or it could simply be that it was oversized at the design stage. If we're generating 2 to 3 times more hot water than is ever going to be required by the process, there's a huge inefficiency there. And if we get a huge size solution, not only the water, but also the body of the heat exchanger, because of the mass of steel, is going to be radiating heat energy out into the plant room. It's going to be taking up a significant footprint of space in the plant room. So we've got a sizing inefficiency there. And remember, if we're using a tube bundle assembly rather than plates, then we're going to get an inefficient A value. And that inefficient A value, as a result of that as a result of that small heat transfer surface area with the storage solution, it means we've got to compensate for that. And we do that by condensing the steam at a higher pressure. And remember, if we're condensing steam at a higher pressure, there's nowhere near as much energy contained within it than there is with steam at a lower pressure. So the process time is going to extend and we get a greater energy inefficiency. But another factor to consider when we're condensing steam at a higher pressure is the fact that we're far more likely to get an insulating film of scale being produced. That's going to further slow down the heat transfer surface area because that insulating film of scale is affecting the heat transfer coefficient, that U value. So again, you can appreciate how those thermodynamic equations all knit together. And of course, if we're holding hot water in storage, we've got that pressure equipment directive and the Legionella L8 issue to contend with. On the subject of manual handling, if we've got to take the heat exchanger apart periodically for insurance inspections and for descaling, we're going to need lifting tackle in the plant room. We're going to need an additional footprint of space around the heat exchanger to be able to allow us to do that. And that's on top of all the benefits that we have by moving towards an instantaneous system that can generate hot water from steam on demand. So we've already mentioned how there's a benefit in ensuring that the heat exchanger is sized to condense the steam at the lowest possible pressure and at the lowest possible temperature. It means with more energy in the steam, it means that the rate of heat transfer can take place very, very rapidly, but it also means it's going to take place far, far more efficiently. The reason being, that condensate that exists within the body of the heat exchanger, that's going to exist at the same pressure and at the same temperature as the steam. So it'd be impractical, but just imagine if we were condensing the steam in the heat exchanger at 6 bar gauge. Well, at 6 bar gauge, it means that the temperature of the steam would be 165 degrees. The temperature of the condensate would be 165 degrees. So as the condensate left the heat exchanger, passed over the steam trap, there'd be a fall in pressure downstream of the steam trap. Flash steam would arise. That flash steam would be vented away to atmosphere. It would result in a significant energy inefficiency. And we're going to cover that topic in a little bit more depth when we present our next topic in the opening weeks after Christmas. Suffice to say that there are a number of key benefits in ensuring that the condensing pressure of steam is held as close to atmospheric as we possibly can. The good news is we can do that by tweaking that air value. If we size the plate pack to ensure that the steam falls in pressure, it will subsequently fall in temperature. We can do that very easily with a plate heat exchanger, but we can't do that easily with a shell and tube heat exchanger. A shell and tube heat exchanger will therefore have a further inefficiency as that flash steam does need to be vented to atmosphere. So there are a number of control options we might use in order to release the energy in the steam. And there are a number of variables that we need to give thought to. And that's going to point us in the right direction when it comes to deciding upon how we're going to control the steam. So for example, if we're in a hazardous area, or if we've got a slow and stable application, we could use self-acting controls. If we've got a sophisticated requirement where we need to hold the temperature at a very, very stable point, or if we need to send feedback to a PLC or a BMS, we're going to want to move towards a control valve. But at the very, very least sophisticated side of the options, we could use an on-off valve for controlling the release of energy onto the secondary side. It's not ideal by any stretch because the valve is either fully open or fully closed, no in between. So it's kind of like having an on-off light switch on your wall at home. The light's either on or the light's off. But for the vast majority of applications, we're going to use a self-acting valve. And a self-acting valve works on proportional control principle. So if we take the example of a vat of water, we're using a steam coil to heat it. With proportional control, it means that, let's say, for example, if we wanted to hold the water at a set point of 60 degrees, it means that the valve will start to open a certain number of degrees above, sorry, a certain number of degrees below 60, and it'll start to close a certain number of degrees above 60. So in this, in the example that you can see on the bottom right-hand side of the screen, we would express that as having a 2-degree proportional band or overshoot. Now, some processors, they can live with that proportional band. Others, they can't. And we can improve upon that and move away from proportional control towards what we refer to as proportional and integral. And proportional control is only available in self-acting valve types. If we want to improve upon proportional control, we need to move towards an actuated control valve. So if we add in integral, then you can see that that's able to predict the required step changes and to start to smooth out that proportional band. We could also further add in derivative control, and by adding in derivative control along with integral and proportional, you can see it basically means that the control valve is going to be able to respond very, very quickly, very, very reliably, and very, very accurately. And that means that pneumatic or electric actuation is going to be more suitable for the vast majority of the more sophisticated processors. We also need to give thought to the shape of the control valve plug and trim. We want to use an equal percentage trim wherever possible on a control valve. And as you can see from the curve over towards the left, it means that an equal percentage trim means that the control valve is going to be in probably the 60 to 80% open position for the vast majority of its operational life. Why is that important? Well, if we'd selected using a fast opening or linear trim, it could spend the vast majority of its operational life operating very, very close to its seats. That's when we're throttling the steam as it's trying to escape the control valve. It's kind of like putting a finger over the end of your hose pipe. And it means that any moisture that's present within the steam is going to have an erosive effect on the plug, meaning a lot of maintenance, meaning a lot of energy that isn't required escaping onto the heat exchanger and affecting the process, but ultimately meaning we've got a huge energy inefficiency. So if we've got a huge buffer of hot water on the secondary side that's taking heat energy on relatively slowly, then a self-acting valve will suffice. But if we're generating hot water from steam instantly and on demand, then that release of energy needs to be controlled very, very accurately and reliably. So we need to move towards a control valve wherever we possibly can. So the good news is if we're moving towards a modern, efficient plate heat exchanger, all of the ancillaries that we've spoken about, the steam traps, the separators, the flow meters, the control valves, the PLC, they can all be brought together on one skid. And that makes it far, far easier for the end user to incorporate into their plant room. Perhaps not only using the steam more efficiently, more reliably, but also freeing up a footprint of space in the plant room for other purposes. And we've also spoken about steam conditioning in the previous presentations we've gone through. You'll remember it's important to ensure that the steam that we're using at the process is free of air. Remember that insulating film of air creates a huge barrier to heat exchange. And it also means if we've got a mass of air that's present, trapped within the steam, we can no longer rely on that pressure to temperature relationship. The process time is likely to extend and extend because of that insulating film. And that's really got its basis in Dalton's law of partial pressures. In layman's terms, think of it as the air is essentially diluting the temperature of the steam, and it makes it more difficult to control the temperature requirement of the process. And we also spoke about the risks that wet steam poses to the process. We've mentioned the separator in some detail when we spoke 2 weeks ago, and we also mentioned why and how wet steam arises. So wet steam is inevitable, but what we can do is pass that wet steam across a separator just before it gets to the process. 2 benefits. The first reason is any moisture that's present within that steam, it can create erosion of those sensitive areas, such as the control valve or the pressure reducing valve. So we get costly downtime, maintenance. It also means if we get a leaking control valve or pressure reducing valve, we've got an excess of unwanted energy passing on to the process, product spoilage, inefficiency. So the first thing we want to do is dry the steam using a steam separator. But the other reason is we've got more energy present within steam when it's dry compared to when it's wet. So it means we're further protecting the efficiency of the process. So the first thing we want to do before that control valve or that pressure reducing valve is dry the steam and fit a little strainer to remove any entrained debris to protect it from damage. Now, steam conditioning ancillaries are quite often overlooked because people fail to appreciate the benefits of having that dry steam. So please, when you get back to your plants over the next few days, just have a look and see if those conditioning ancillaries are there. We want the steam to be as clean, dry, and free of air as we possibly can. So once we've dried the steam, we've reduced the pressure. We can use a pressure reducing valve. We can use a control valve to do that. As far as a control valve is concerned, it's critically important that it's been sized correctly. We size a control valve on the mass flow rate of steam, not on the line size. So if you've got an 1.5 inch line, for example, we'd expect that a 1-inch control valve would be sized correctly. We size on the mass flow rate. And that's principally because, if you'll remember, we want to ensure that the control valve is held in the 60 to 80% open position for the vast majority of its time, where we're not going to get issues caused by erosion or excess wear and tear. And I just want to go back to one of those basic thermodynamic equations very, very quickly. So the equation above to the left, it really demonstrates how we can calculate how much energy there is in a mass of steam. So for example, the Q value, that's the heat transfer rate. The M value, that's the mass flow rate of steam in kilograms per second. And the HFG, that's the enthalpy of evaporation that we can determine if we know the pressure of the steam. The dot basically denotes that it's a moving or a mass flow rate. So in other words, if we know the pressure of the steam going on to the heat exchanger, then we know the enthalpy of evaporation. So if we look over towards the right-hand side of the screen now, let's say we know the Q value. Let's say we've got that from the badge of the heat exchanger. And we need to determine how much steam is required to heat the process. Well, we can rearrange that thermodynamic equation as we discussed earlier. So for example, if we know that we've got a 300 kilowatt duty, we know that we've got 2000 kilojoules per kilogram enthalpy of evaporation in the steam. Well, we can rearrange the equation and we can determine that we actually need 540 kilograms per hour of steam to satisfy the process. So basically, we've used one of those equations to calculate not only the steam demand, but also the size of the control valve. So another thing that we need to remind ourselves, and there's a common theme occurring here, is the condition of the steam. We want to ensure that the steam is kept as dry as we possibly can. Remember, the steam tables and therefore the heat exchanger, it can only be sized on a value of steam based on a dryness fraction of 100%. So if we've got steam that is 50% dry, 50% wet, there's going to be 50% of the energy present in that mass of steam. And if we've further got a mass of air that is entrained within that steam, then the moisture, together with the insulating effect of the air, it means that that rate of heat transfer is likely to extend and extend and extend. So just to summarize what we've gone through today, whenever we're talking about steam for heat exchange, it's that enthalpy of evaporation. It's the energy that we add to the boiling water that is used for heat transfer purposes. The condensate, it's got no value at the heat exchanger, but it does have a value as hot water if we can get it back to the boiler house. We know that steam gives up its heat energy evenly across the heat transfer surface area. We can know that we can release the energy present within the steam simply by manipulating the pressure. And the important thing is, we understand that we need to do absolutely everything we possibly can to ensure that the steam arrives at the process as dry and as free of air as we possibly can. So please remember those conditioning ancillaries that should be present at all times. So as you can see, the final point there is we want to ensure that we've got efficient and accurate removal of condensate from the heat exchanger. And we're going to look at both steam trapping and condensate management to discuss that issue further in the new year. So please don't hesitate to make a note of the remaining CPD presentations in the series, where we'll continue with our journey. But on that note, I'd like to thank you very much for your time, for joining me tonight. Thanks again to Brian, thanks to IMEC for arranging. If you would like to receive a PDF copy of the slide pack that we've gone through tonight, and an attendance certificate, please don't hesitate to drop me a line. And please also give some thought to following me on LinkedIn, where we post periodic tips of how to get the best out of your steam distribution network. Thank you very much. Any questions tonight, Brian?
Thanks, Dan. I've got 3 in so far. Those people that are still online, if you'd like to send them any questions in by chat. The first question, in a previous lecture you did, Dan, I don't know if you can cast your mind back, you mentioned about reversing the direction of steam every 50 meters. Does that ring a bell?
No, that was every 30 to 50 meters. That's where we should have a steam trapping station. And the purpose of the steam trapping station is really to ensure that we're removing the condensate losses that exist when steam gives up its heat energy to the distribution pipework. So that 30 to 50 meters, it's a very, very broad rule of thumb for good working practice to ensure that the condensate is removed from the distribution pipework periodically, so we can get it to the process as dry as we can.
Okay, thanks for clarifying that, Dan. Also, how is the U value determined that's got a mention in tonight's lecture?
How is it determined?
Yeah.
There's engineers' notebooks, charts on the internet. Typically different materials of construction, different thicknesses of materials, the likelihood of scaling, they can all affect the U value. For example, copper and stainless steel would have different U values. So that's generally something that the manufacturer would advise. And it's for that reason that any existing heat exchanger will have that information badged on it or present on the thermal energy data sheet. It's important to bear in mind that the U value will only apply once the heat exchanger is brand new and free of scale or any other debris that could be creating a barrier to heat exchange.
Okay, thanks, Dan. And final question, at least for now. In the slideshow, you had a picture of a single pressure vessel. Not sure whether there was just a query over some discontinuity on the outside of it, or does that ring a bell? In tonight's slideshow, was there a slide of a single pressure vessel?
As in what, the calorifier?
Yeah, could be, yeah. And
no, they're not. I mean, calorifiers, and they are still very much in operation. They are process specific. A minority of processes will require a huge amount of hot water in a very short period of time, for example, washdown. So there is still a requirement for storage solutions. But it's important to understand the benefits of minimizing that hot water being held in storage on the secondary side wherever we possibly can for efficiency purposes.
Brilliant, thanks. Final non-technical question. The final presentation, the date of it, you couldn't just bob your slide back up. Is that possible with the dates of future lectures? That's brilliant. So, yeah, we're up for time. So just remind everybody, this was an IMechE lecture by Dan Wells and hosted by Project Solutions. And although I haven't mentioned the IMechE very much, I belong to the Western area. And if anybody wants to get involved with IMechE activities, feel free to contact me on LinkedIn. So as we're closing the show tonight, I'd like to just wish everybody a Merry Christmas, as long as you comply with government guidance and guidelines, and have a small one. Thanks to Dan and the guys back in Project Solutions in the back office, and Nikki, the IMechE admin support for organising. So any final remarks, Dan?
No, I'd just like to echo that, and thank you all for joining in. Hopefully you'll find the time to join us for the remaining presentation in the series in the new year. And I'd like to wish you all a good Christmas.
Yeah, thanks, Dan, and thanks for all your help with this. So, guys, have Christmas off, and next lecture's on the 13th of January, usual time, 6:30. Loads of messages coming in saying thank you, Dan, and have a Merry Christmas. So, Merry Christmas to you guys, and we'll close the show at that.
Great.
Good
Thank
night.
you very much.
Thanks,
Thank
Dan.
you. Good night.
Bye.